Hi everyone, and welcome back to Return. Isn't it a miracle? Light from billion years ago travels across the void, is captured by a telescope, converted into data, beamed across millions of miles of empty space, and on your screen perfectly. But what happens when the universe fights back? Every system, from the emptiness of space to the copper in a wire, is filled with noise, with chaos. This chaos is the fundamental enemy of order, of knowledge, of connection. How do we send a message through the storm and know it will arrive whole? How do you even measure a message? How much stuff is in a picture, or a sentence, or a single thought? In 1948, a quiet genius at Bell Labs named Claude Shannon gave us the answer. He gave us a weapon against the chaos. He gave us a unit to measure thought itself, the bit. But he gave us something more. He gave us a new way to see the world, a powerful, almost philosophical concept called entropy. And here is the twist you won't see coming. This 75-year-old idea is the beating heart of the most advanced technology on earth today. It is the ghost hiding inside every artificial intelligence. Today, we are not just going to talk about technology. We are going on a journey to the very foundation of our digital world. By the end, you won't just understand how your Wi-Fi works, you will understand the universal laws that govern information. You will see Shannon's ghost in every line of the text ChatGPT ever writes. Before Shannon, engineers were fighting a ground war. They were building better wires, stronger amplifiers, bigger antennas. They were trying to overpower the noise. Shannon's genius was to float above the battlefield. He ignored the hardware and created a simple, universal blueprint for any communication ever. It starts with an information source, your mind, a book, a hard drive, the place where the message is born. That message goes to a transmitter. This is the encoder. Your mouth turning thoughts into sound, a modem turning data into radio waves. It packages the messages for its journey. The message travels through a channel. This is the medium, the air, a fiber optic, the vacuum of space. But every channel is plagued by a noise source. This is random interference, solar flares, thermal energy, the chaos of the universe which corrupts the signal. This is the villain of our story. At the other end, a receiver catches the corrupted signal and does its best to decode it, performing the inverse operation of the transmitter. And finally, destination, where the message is understood. This blueprint was a revolution. Talking, television, space probes, it is all the same process. By creating this abstraction, Shannon could stop asking, how do we build a better pipe? How do we build a better communication system? And start asking a much deeper question. How much message can we send through any communication system, no matter how noisy? To answer that, he had to first measure the message itself. And it all began with a simple guessing game. Let us play a game. I've chosen one of these 16 boxes. You have to find it by asking only yes or no questions. The worst strategy, is it box 1? Is it box number 2? That could take you 15 questions. The best, you cut the problem in half. Is it in the top half? Yes, bam. With one question, you have eliminated 8 possibilities. Is it in the left half of what is left? Yes, bam. 2 questions and only 4 possibilities remain. 2 more questions and you will have it. 4 questions, yes. 4 yes, no answers to resolve uncertainty about 16 possibilities. Shannon, building on earlier work, said that the number of questions is the amount of information. He called the information in one yes-no answer a binary digit we call a bit. 1 bit is the information needed to choose between 2 options. 2 bit for 4 options and 4 bits for 16 options. The information in bits is the logarithm base 2 of the number of possibilities. It is an elegant additive measure. But this only works when every box is equally likely. What happens when the universe is biased? Which weather report gives you more information? The one from Sahara that says it is sunny, or the one from London that says it is sunny? The Sahara report is boring. It is predictable. You haven't learned much. But hearing it is sunny in London, that is surprising. It would have been anything else. This is the profound insight. Information is surprise. A probable event is unsurprising. It carries low information. An improbable event is surprising. It carries high information. Shannon needed a way to measure the average surprise of a system, and he called it entropy, as suggested by his friend John von Neumann. This formula might look terrifying, but it is beautiful. Here, Pxi is just the probability of an event. Log base 2 Pxi part is the surprise, the number of bits for that single event. For a rare event, this value is huge. We simply calculate that surprise value for every possible event, weigh it by its own probability, and add them all up. The negative sign just flips the result to be a positive number. So, the entropy is the probability weighted average surprise. For a coin flip, if the coin is biased to always land on the heads, the outcome is certain. 0 surprise, 0 entropy. But if it is a fair coin, 50 by 50 chance, we are maximally uncertain. We have no idea what is next. The entropy is at its maximum, exactly 1 bit. This single beautiful curve quantifies uncertainty itself. This is all great in theory, but let us make it real. We can write a simple Python function to calculate entropy. Look at the results. The fair coin gives us 1 bit of entropy, just as we saw on the graph. The biased coin gives us less than half a bit of entropy. It is much more predictable. The fair die with 6 equally likely outcomes has an entropy of about 2.58 bits. This makes sense. It is more uncertain than a coin flip. Now let us apply this to language. In English, letters are not equally probable. E is the most common while Z is rare. Shannon noted that this statistical structure means language is redundant. He estimated the redundancy of English is about 50%. This means about half of what we write is determined by the statistical rules of the language, and the other half is our free choice. This redundancy is why data compression in .zip, JPEG or MP3 files works. We can use shorter codes for more frequent symbols like E and longer codes for rarer ones like Z, just like Morse code does. The entropy tells us the ultimate theoretical limit of how much we can compress that data. The lower the entropy, the more compressible it is. But Shannon did not stop at single letters. He imagined systems that could predict the next letter based on the one before it. Okay, so we can now calculate the entropy of a source. We label it H. It is measured in bits per symbol. This is the rate at which our source produces information. But every channel has a speed limit, a maximum rate at which it can reliably transmit bits. Shannon called this the channel capacity, labeled C. So now we have two numbers, H, the entropy of our source, and C, the capacity of our channel. The climax of Shannon's entire paper, his masterpiece, was the noisy channel coding theorem. It connects these two numbers with one elegant world-changing rule. For centuries, engineers thought noise was an unbeatable foe. They believed that for any real-world channel, errors were inevitable. The only way to reduce them was to crank up the power. Shannon proved them all wrong. He proved that if the rate you are producing information H is less than or equal to your channel's capacity C, you can transmit your data with an arbitrary small number of errors. Think about that. As long as you don't try to go too fast, you can achieve near perfect communication. Errors aren't inevitable. They are the price you pay for exceeding the speed limit. But if h is greater than c, it is impossible. You are fundamentally trying to create information faster than the channel can carry. The channel will overflow, the data will be lost. This was the Holy Grail. It gave engineers a target. Calculate the entropy of your source, and you know the absolute minimum channel capacity you need. This insight drives everything from 5G to data compression. .zip files, JPEG files, MP3s, they all work by measuring the entropy of the data and using clever codes to get its entropy h as low as possible so it can fit through smaller pipes. This theorem separated the information from the hardware and gave us the universal speed limit for all communication. And it is this exact framework that brings us to the ghost in the modern machine. To see Shannon's ghost in the AI, we need to look at the AI in two different ways. First, how it writes, and second, how it learns. And in each case, it plays a different role in Shannon's blueprint. Let us start with the trained AI, that is generating text. It is acting as next word prediction engine. When it does this, the LLM itself is playing the role of the information source. It looks at the sequence of words so far and generates a probability distribution for what comes next. The information it produces is a resolution of uncertainty about that next word. And the entropy of its own probability distribution tells us how uncertain the model is. If it sees the cat sat on the probability for Matt is huge. The model as a source has low entropy, it's confident and predictable. If it sees the meaning of life, the probabilities are widespread. The model as a source has high entropy. It is uncertain and surprising. This is why in AI we use perplexity, which is just 2 to the power of the model's entropy. And when you adjust an AI's temperature, you are directly controlling the entropy of the AI as a source. A low temperature makes it less random. A high temperature makes it more creative, more surprising. So that is how the AI writes. But the deeper connection to Shannon comes from how it learns. For this, we have to look at the training process. And here, the roles shift completely. The goal of training is to distill the knowledge of the world into a single program. Let us look at this through Shannon's blueprint. Our information source is now the training data, a massive chaotic snapshot of the internet. The amount of information, patterns and knowledge here represents our entropy, H. All of that information must be transmitted to the model. The channel in this case is the neural network's architecture itself. Its channel capacity is determined by its number of parameters. A 7 billion parameter model is a narrower pipe than a 70 billion parameter model. It has a fine capacity to hold information. The transmitter is the training algorithm. Its job is to find brilliant encoding scheme to adjust the model's parameters or weights to compress the essential signal from the source data so it fits through the channel. Now Shannon's golden rule. H less than equal to C becomes the fundamental law of training AI. If H is greater than C, that is, if the essential information in the data is greater than the model's capacity, you get underfitting. The model is too small. The pipe is too narrow. You can't learn the patterns. If H is less than equal to C, the model is large enough. The challenge now is for the transmitter, the training algorithm, to be smart enough to encode the true signal of knowledge while ignoring the vast amount of noise in the training data. If it just memorizes the noise, it becomes overfit and useless. So you see, the LLM's existence is a beautiful duality. When it writes, it is an information source governed by entropy. But to exist at all, its architecture must first act as a channel, constrained by a finite capacity through which the knowledge of the world is poured. This entire epic struggle of building and training AI, of model sizes, of data quality, of underfitting and overfitting is a perfect echo of the battle Shannon first described in 1948, the timeless battle of signal versus noise. From a simple guessing game to the architecture of artificial thought, Shannon's paper did not just give us tools to build better phones, it gave us a new language to describe the universe. He saw that the opposite of chaos wasn't order, it was information. He taught us that information isn't a thing like a rock or a chair, it is a property of a system. It is a measure of the freedom of choice one has when constructing a message. It is a measure of resolved uncertainty. And that ghost, the ghost of Shannon, it is in the compression that lets you stream this video. It is in the error correction that keeps your data safe. And it is in the very heart of AI, which, in its endless attempt to predict the next world, is simply trying to calculate the entropy of human thought. Claude Shannon gave us a way to fight the noise, to send a signal through the storm, and in doing so, he gave us the blueprint for building new kinds of minds, all from a single beautiful idea born in 1948. See you next time. Thanks for watching.